Alrighty, folks, today we are going to be talking about magnetic fields. So what you are seeing right now is actually a diagram of the Earth's magnetic field, which we will talk a little bit more about at the end of this lecture. Alrighty, here we go. Go ahead and set up your notes for today. Our essential question is, how does a magnet affect its surroundings? We have 4 guiding questions today. What is a magnetic field? What is the shape of a magnetic field? Where are magnetic fields strongest and weakest? And why does a compass point north? All right. I can explain how magnetic poles interact. This is our learning target again for today. Alrighty, let's start off with this. Where does the word magnet come from? Well, there are actually 2 ideas about where the word magnet comes from. It is either the ancient Lydian city of Magnesia ad Sipylum, which is the modern-day Manisa, Turkey, which you can see right here on this map, or it comes from the Magnesia region of ancient Greece, which you can see right here on this map. Magnetes from Magnesia ad Sipylum colonized a region that was the primary source for mysterious stones that could attract and repel each other, which would be magnets. In Greek, magnetus lithos means Magnesian stone, and magnetite, which is a magnetic ore, was produced in the Magnesia region of Greece. So, the word magnet comes from one of those 2 sources. Alrighty, folks, today we are going to begin with a little bit of an interactive demonstration here. So we are going to be doing a draw it. What I need you to do is I need you to turn to the bar magnet diagram in your packet. It looks like this right here. If you do not have a packet printed off, just go ahead and draw a rectangle like this, and on the left side label it S for south, and on the right side label it N for north. Now, what we will be doing is placing a compass near the bar magnet, and we will observe the direction that the red point of the compass points. So you will then draw an arrow pointing in that direction on your paper where the compass is placed. I will show you in just a moment what this means. I'm going to do this in person in a demonstration, and I'm going to give you the opportunity to do this digitally. So you will then move the compass slightly and do this again, and you're going to do this at least 20 times, drawing 20 arrows all around the magnet. So I'm going to show you what this looks like in real life, and then I'm going to give you the digital opportunity to do this. And I will have a video showing the entire process for this in the folder for today if you are confused about what you are supposed to do. So let's go ahead and watch the demonstration. Alrighty, folks, so what we are doing is we're going to take a bar magnet and we're going to place a compass next to it. And then on our diagram, we are going to record the direction that the red arrow points. So for example, if I placed it right here, I would go ahead and say, hey, the red arrow is pointing straight down. So I would draw a red arrow straight down like that on my diagram. Then I would move it and I would say, hey, when I put it there, the red arrow is pointing a little bit down to the left. So it's not exactly centered. So I would draw a little arrow like that right there. So go ahead and on the online version, follow the instructions on the following page. Alrighty, folks. Now that you have seen what it is we are doing, go ahead and open up the web page that is shown on Nearpod, and you will see a demonstration that looks like this. I have gone ahead and blown this up to full screen. So right here, you have a compass, and right here, you have a bar magnet. So what you're going to do, like we showed, is you place the compass on the bar, or near the bar magnet, and what you see is that the compass, and a compass, as we said, is a small magnet. It points in a certain direction. So you are going to draw the red arrow pointing here. So you would draw this on your paper. Then you're going to move the compass slightly, and now you would draw that the red arrow is pointing here. Move it slightly again, do that. So go ahead and move the compass all around and draw at least 20 arrows showing where the compass points on your diagram. Pause the video, do that, and then come back after you've done that. Alrighty, so what you just drew is what is called a magnetic field. A magnetic field is the space around a magnet where it applies magnetic force. It is strongest near the magnet's poles, and you'll see that the lines are closest together here. And it is it gets weaker as you get farther away, and you can see that the lines are farther apart. So it will either attract or repel another magnet that enters into its field, and we'll show in just a moment what that looks like. But you should have something that looks approximately like this, and you can see that the arrows point from north over towards south. So there you go, that's a magnetic field. Alrighty, so you can actually, besides just using a compass, you can actually visualize magnetic fields using iron filings. So I've got a bunch of different ones here. So you can see right here in a simple bar magnet, you can actually see the magnetic field shown using iron filings. However, what we can also see is what happens when you have two magnets pointing towards each other with their different poles. So right here, this is when you have a north pole facing a north pole, basically the same pole facing. You will notice that the area between those two poles is completely void or empty of magnetic or of iron filings. This is because there is no magnetic force here, which is what you would expect because like poles repel each other. You can see down here that this is the magnetic field, what it would look like with arrows. Over here, you can see opposite poles next to each other, and what you notice is that the iron filings, there are a bunch there, and that's because the area between those two poles, the magnetic field there, becomes stronger when you place two poles next to each other, meaning that opposite poles are attracted to each other. So you can see right here that unlike poles attract each other. In your notes, I would like you to make sure that you have the diagrams of just a single magnet and its magnetic fields, opposite or unlike poles attracting each other in their magnetic fields, and like poles repelling each other and their magnetic fields. So I'm asking you to draw these three diagrams. So go ahead and make sure those are in your notes. The Earth is a giant magnet. So we talked about what the interior of the Earth looks like and the fact that its core is iron. And so because of that and the movement of the core, the Earth actually acts as a giant magnet. And the magnetosphere is the area surrounding the Earth that is influenced by its magnetic field. We also talked about that when we talked about the atmosphere and the layers of the atmosphere. The magnetosphere kind of being the uppermost regions of what we consider the Earth's atmosphere. So, why does a compass point north? Well, a compass is a tiny magnet, and the Earth is a much larger magnet. And so that means that the tiny magnet of the compass is going to point towards the opposite pole of the Earth's magnet. Now, here's a little thing that's going to blow your mind. Think about the fact that a compass magnet, that red point that points north, that red point is the north pole of our compass magnet, and it is pointing towards the pole on the Earth that it is attracted to, which means that it is pointing towards the magnetic south pole of the Earth. What that means is what we think of as north is actually the south magnetic pole of the magnet. I will give you all a moment to pick your jaws up off of your desk because of how I just blew your mind. I know, crazy stuff. So, we still call north, north, and south, south, but that is technically incorrect. So, another thing to note is that the geographic North Pole is going to be at the top center of the Earth, and the geographic South Pole is at the bottom center of the Earth. And that just is kind of nice for simplicity's sake. However, in reality, the magnetic North Pole actually is at 81 degrees north. So it's not the tippy top of the Earth. It's actually somewhere over in northern Canada. And that's because the Earth's magnetic poles do not go directly along this line. They actually line up with how the core spins. So there is actually a difference between what is magnetic north and what is geographic north, and this is what we call magnetic declination, the variation a compass shows between geographic north and magnetic north. So we can see here the Earth, and then what you are looking at here is the Earth's magnetic field, and this is why the Earth's magnetic field is important. So we talked about the fact that electromagnetic radiation, or the electromagnetic spectrum, is how light travels, and that the sun gives off electromagnetic radiation. Some of that is really useful, like the infrared or the visible light that we used to see, but some of it's really dangerous. And actually, the Earth's magnetic field protects us from some of that electromagnetic radiation and shields us from it. So you can kind of see a diagram of that happening right here. All right, folks, go ahead and pause this video, take a 4-question quiz, and then come back and I'll go through the answers with you. The area that surrounds a magnet where it can push or pull is its magnetic field. Where is a magnetic field strongest? It is strongest at both poles of a magnet. If two magnets are placed next to each other, opposite poles facing each other, as shown in this picture, the magnetic field between the poles would be stronger than normal because opposite poles are attracted to each other. The difference between geographic north and magnetic north is called magnetic declination. So, if you answered those questions as I just went through, you should have gotten 100%. So, that's it for our lecture today. If you have any questions, please make sure to submit them to our discussion. Have a good day, folks.